Good morning. Can you hear me now? It is a pleasure to be here. Thank you to the organizers for inviting me to participate in this very fascinating set of lectures and discussions this week. And thanks to all of you for being here to listen to me as I talk about the availability of something called critical raw materials. And as you can see by my title, I've organized my comments around four topics or four perspectives. The central question around which I'm organizing my comments is the following. Will constraints on the availability of critical mineral-derived raw materials limit the energy transition? Now, by energy transition, I obviously mean the transition from conventional fossil fuels to low or no carbon sources of energy. Now, by critical raw materials, well, I will speak to that in more detail in a moment, but what we're really talking about is the reality that clean energy technologies, low or no carbon technologies, will require mineral raw materials that up until now have been used very little, if not at all, and in fact will require increased mining of certain raw materials. So we have this seeming contradiction that we need more mining to facilitate the energy transition. I view it not so much as a contradiction, but as a challenge. So that was the question in words. Sometimes a picture is more useful than words, and my question for you is, what is this a picture of? And does anyone know? Avatar, very good. I was hoping someone would know. The 2009 movie that focused on what? Does anyone remember? I can't remember this character's name. I think Neytiri or something like that, but I'm not sure. But what was one of the themes in Avatar? Unobtainium. Unobtainium. And the specific unobtainium in this movie was a room temperature superconductor. And the idea of unobtainium is what? A difficult to obtain, a rare, costly raw material that provides special properties. And that's another way to think about this presentation. And as we think about the energy transition, we might ask the question, are any of the following elements unobtainiums? And so if we think about energy storage, we have lithium and cobalt and graphite in the current lithium-ion battery technologies. In emerging battery technologies, we have things like vanadium and manganese. If we think about high-efficiency motors, the current technologies require very small, very powerful magnets that rely on the four rare earth elements indicated in this slide: neodymium, praseodymium, dysprosium, and terbium. Or if we think about fuel cells and the hydrogen economy, we have elements like platinum, palladium, and rhodium among the platinum group elements. We have lanthanum and cerium from the rare earths, and yttrium. We have cobalt again, and we have gadolinium, another one of the rare earths. Are these unobtainiums? In terms of solar technologies, in the silicon-based world, we have things like silver, nickel, and tin. In the CIGS, or copper, indium, gallium, selenide world, we have indium, gallium, and selenium. In the CAD-TEL, or the cadmium telluride world, we have tellurium. Are these unobtainiums? So that's the topic that I want to talk about in the next few minutes. And so the first of my four perspectives is to define critical raw materials more precisely. In words, a critical raw material, at least as this term has come to be used in the specialist language in this field, a critical raw material has three characteristics. It provides essential functionality in a modern engineered material or system or technology. It is difficult to substitute away from, at least in the short to medium term, and it has supply chain risks or concerns about longer term availability or unavailability, the unobtainium aspect to this. And it's the combination of the three things that have focused people's attention on where will we get these materials to facilitate, in the case of clean energy technologies, the energy transition. Again, in the spirit of pictures rather than words, visually, this diagram is often used, this type of diagram is used to illustrate criticality in the critical materials sense, where we take those three dimensions and collapse them, the three definitional characteristics, and collapse them into two dimensions. So we have impact of a supply disruption on the vertical axis. That importantly captures this idea of important functionality. And then we have supply risk or supply chain risk on the horizontal axis. And then the ease or difficulty of substitution can go either on the horizontal axis or the vertical axis, depending on how you actually do the scoring in the analysis. And as you go from the lower left-hand portion of the diagram to the upper right-hand portion of the diagram, a material or an element or a mineral becomes increasingly critical in this more specialized definition of the word critical. Now, a bit of background. My wife and I moved recently, and in cleaning out our house, in 5 or 6 different drawers, I uncovered 7 or 8 different cell phones. And I lined up 4 of them. I didn't have room for 7 in a picture that was large enough to actually allow you to see all 7 or 8. The cell phones that I uncovered from oldest to newest. I don't go quite back as far as the first version, the Motorola of brick phones that you needed a briefcase to carry. But I start with the Nokia. I'm not quite up to the present. That's an iPhone. I think that was an iPhone 5. I have the iPhone 8 here, the replacement from about a month ago. But as you go from the left-hand side to the right-hand side of this diagram, you go from a product that contains roughly 20 to 30 elements in the periodic table of elements to a product that contains approximately 70 of the elements in the periodic table. So we go from 20 to 30 to roughly 70 elements in the periodic table. And furthermore, realize that there are only something like 81 or 82 elements in the periodic table that material scientists draw upon when designing materials, systems, and technologies. So the smartphone basically contains the entire periodic table of elements in the technology that we use. Now realize, what do we get when going from 20 to 30 elements to 60 to 70 elements? We get increased functionality. And in fact, most of us probably don't even think of this really as a phone. What do you use it for? I'm sure some of you are using it for what as we speak. Maybe it's note-taking, but my guess is it's email messages, text messages. Maybe someone's taking a picture of me, probably not. But we hardly think of it as a phone. Well, the increased functionality is what we get by using more elements from the periodic table of elements. And so we can think about this expression, or the expression, the periodic table under siege. The growing complexity, the material complexity of modern technologies brings with it significant benefits, but it requires mineral-derived resources, many of which we've not used in significant quantities before. The illustration of the smartphone is replayed throughout many, if not most, modern products. Most of these elements are used in very small quantities, so very little of those additional, the indiums, the galliums, the neodymiums in a smartphone make up a very small weight percent of the typical phone, and therefore I think of, in the realm of images, critical materials as vitamins or spices. Vitamins, things that we take in very small quantities that we hope provide essential beneficial properties to our bodies. Spices, small quantities, provide essential properties to the foods that we like to eat. So too it is with critical materials. So that's my first of four perspectives, this idea of what is a critical material? Critical materials actually as spices and vitamins as opposed to unobtainiums. Okay, my second topic. We've talked about supply chain risks and concerns about availability, and so my second topic is a proposition, not a question. And that is, we are not running out of mineral resources. Rather, the risks to availability, both in the short term and the long term, are more nuanced, more multifaceted. So let me start with the first part of that proposition. We are not running out of mineral resources. In my view, it's an unfortunate fact that too often discussions about resource availability start from the proposition that we are rapidly using up our mineral raw materials and that resource extraction is fundamentally non-sustainable. And then the discussion proceeds from there. I think that is an enormous distraction. There is little, if any, I would say almost zero evidence that we are in danger of running out or using up mineral raw materials. Sure, there is a limited amount of mineral resource in the Earth's crust, but all the available evidence that I'm familiar with suggests that human use of that resource is trivial compared to the total quantity available. So instead, and we could have another 1-hour lecture on that topic, but that's not the topic for the rest of this talk. Rather, let's talk about these more nuanced issues. I think it's convenient to divide the risk factors to availability, risk to availability, into two categories, short-term and longer-term. And I've listed the short-term here to go through them relatively quickly, and then we'll talk about the long-term risk factors in a little more detail. So we have risk of demand shock, the idea that when there's a small existing market for a material like neodymium in magnets, undergoing rapid growth, the market can be caught by surprise and disrupted and discourage the use of that material. So that's a risk factor. Lack of supply chain diversity. About 5 years ago, there was a lot of public concern about the availability of rare earth elements, the lanthanide elements at the bottom of the periodic table. That was principally because of the volatility in the market caused by the extreme geographic concentration of production of rare earths in one location, one country, which happened to be China. And so that's a second risk factor. Reputational risks have become more prominent in the more recent past as we think about battery materials and cobalt. Cobalt, more than half of which, half of world production occurs in the Congo, some of which involves child labor, some of which funds armed conflict, and as a result, users of cobalt not wanting to use cobalt mined in Central Africa because of risks to their corporate reputations. And then finally, the factor that I've listed as plus or minus, co-production risks and opportunities. It's plus or minus not because it's a risk, it's plus or minus because I go back and forth about whether it's a short-term risk or a long-term risk. Here I include it as a short-term risk, but it could easily be in the other category. And what's the idea here? Well, if you understand this, you can consider yourself halfway to being a specialist in the topic of critical materials. And the idea is the following. Many of these so-called critical raw materials are produced as minor byproducts along with other more major or the principal materials that are mined at that resource. So tellurium, used in cadmium telluride thin films, are produced as minor byproducts in the production of copper. The copper operation is designed, planned, optimized around recovering copper, and then, oh, by the way, maybe we'll recover some tellurium. The same thing is true with gallium and bauxite and aluminum production, with indium and its association with zinc production, and many of the other rare metals that I listed earlier. This is a supply risk not because the material is not available, but rather that the availability of the minor byproduct is influenced not just by the economic and commercial considerations of the main product, copper, zinc, aluminum, or let me back up, I said that wrong. The availability of the byproduct are influenced and determined not just by the economics of that particular market, tellurium, indium, or gallium, but also by the developments of the associated main product, copper, zinc, or aluminum. And so the supply function is complicated, and just because the price of the byproduct, tellurium, gallium, indium, goes up, that may not lead in short order to increased production and availability because the economics of its availability are determined largely by the economics of the associated main product. So those are a number of the short-term risk factors. What about longer term? Well, here we are more fundamentally constrained, and the topic of this session is constraints, are geologic and technical in nature. So geologic constraint being the idea, does it exist in the Earth's crust or in outer space or in the mantle of the Earth? Technological, if it exists, do we have a technology capable of extracting it? And these are fundamental constraints that even economists recognize. And I felt a little bad yesterday. I thought economists were under attack. If you listen to some of the lectures yesterday, and I would argue that was a bit of an exaggeration, but I accept the criticism. So back to geologic and technological scarcities, a starting point for these discussions is average crustal abundance. It seems obvious that we ought to use, that the more abundant elements on average in the Earth's crust should be more available. And here we have a plot of average crustal abundance on the vertical axis, atomic number on the horizontal axis. We have the common rock-forming elements like iron, aluminum, and silicon on the upper left-hand corner in green. That probably means good. All the way down to the rarest elements, rarest in terms of average crustal abundance, in the lower right-hand portion, things like platinum, the platinum group elements, and a number of other of the materials that often are described as critical or for which there are concerns about unavailability. Well, let's test the proposition. We might ask the question, how good a predictor is average crustal abundance of at least one important measure of an element's availability, which is price. Now, let me admit right off the bat, price is not a perfect indicator of availability, but it's not a bad first approximation. And so what if we plot a material's price over the last 100 years relative to average crustal abundance? This is what we get. So we have crustal abundance on the horizontal axis, prices on the vertical axis, and as expected, as crustal abundance there's an inverse relationship between price and crustal abundance. The less abundant a material, the left-hand side of the diagram, the higher the price. But the scatter is pretty wide around this diagram. And so, and this is work, unpublished work that I and a graduate student have done. So we asked then, well, what else might be at work here? And we thought, well, maybe there's something to do with energy requirements in extracting and recovering these elements. And so we did a plot of that. And what do you find here? Here we have energy requirements in production plotted against prices. And we have the expected upward relationship that the more energy that's required, the higher the price. But I think more significant relative to the previous diagram is the very narrow scatter. There's a much stronger correlation between energy requirements than there is with average crustal abundance. And in fact, if you do more sophisticated statistical analysis, which we've done, energy requirements explain about 30%, 25 to 30% of the variation in prices. Average crustal abundance, only 10 to 15% of the variation in prices. And then the remaining 40 or 50% is other factors, which then leads to this issue of technological scarcity. It's not so much average crustal abundance, geologic scarcity, as it is technological, and how can we reduce the energy use in production, which was highlighted in a Nature article 2 years ago called 7 Chemical Separations to Change the World. If you can read the subtext there, purifying mixtures without using heat would lower global energy usage, emissions, and pollution, and open up new routes to resources. And one of the 7 highlighted in this paper was rare earth metals and their separations from ores and in turn from each other. The rare earth elements like to be together, and yet their uses require separated individual rare earth elements in most cases. We also have environmental and social impacts as a long-term risk factor. So if geologic risk is, does it exist in the Earth's crust? If technical risk is, can we get it out? Environmental risk is, can we get it out with environmental consequences that are acceptable to human beings in the environment? And social impacts represents this idea, can we extract and recover and use a material with social impacts on local communities, native populations, and others in ways that are acceptable? And then my third and final long-term risk is insufficient investment. Insufficient investment, not just in the actual production facilities, but in all 4 of the risk factors identified in the previous 2 bullet points. The geologic, does it exist, risk factor, the technological risk factor, do we have chemical separations that can eliminate the need for pyrometallurgical operations for extraction and recovery, investment in environmentally friendlier ways of production in ways that are acceptable to local communities and society generally. So that's my second of 4 points, and I realize my final 2 points are rather much quicker, so don't worry that I'm droning on endlessly on a topic that I could drone on endlessly about. So that was the second topic. We're not so much running out of mineral resources as we are facing other more nuanced, more complicated risks. Third, and somewhat more briefly, let's ask the question, what's critical for carbon abatement? This is unpublished research that we've done at Colorado School of Mines. It's work that takes the world as its perspective. It focuses on a particular time frame, 2018 to 2014, which, as we've heard from the climate change discussions, is a critical period in terms of reducing, if not eliminating, greenhouse gas emissions. And we focus on 9 technologies and 27 elements. These are the 9 technologies: photovoltaics, wind, so on and so forth. These are the 27 elements. 10 of which are rare earths, 17 of which are other. They're all arguably minor metals, specialty metals that we talked about earlier. And here's the figure. Now, I'm not going to go through this in detail. There's a picture is worth 1,000 words. In this case, it may be worth 10,000 words, but that's not the point. The point is we've operationalized that diagram that I showed you previously. We have, on the vertical axis, impact of a supply disruption, which reflects what in this particular case? What's at risk if supply chains of essential raw materials are disrupted? It's carbon abatement at risk. So the higher an element plots on this element or on this figure, the more carbon abatement, the more tons of carbon emissions abated are at risk. This relates importantly to our estimates of carbon abatement potential for the period 2018 to 2040, using technology deployment scenarios from entities like the International Energy Agency. And you find that electric vehicles represent about 50%, roughly half of the potential carbon abatement at risk if supply chains are disrupted. Nuclear power, maybe perhaps surprisingly, is about a quarter. And these relate to carbon emission reductions for nuclear power plants that are designed and under construction and planned at the moment. Most of these are in China, but it's a non-trivial source of carbon abatement. And then the remaining quarter is everything else. Supply chain risk. Here we actually score the horizontal axis not by the long-term factors, because 2018 to 2040 really is not long-term. It's on the basis of things that we know about today. It's resources that we know about today. It's lack of supply chain diversity. It's the co-production risk that I talk about, and it's the risk of the demand shocks. We score these the supply chain risk relative to iron and copper. And then the final thing that you may have wondered about are these contour lines. These are ISO risk lines from really classical risk analysis, where we have a probability of a disruption, the horizontal axis, times the conditional outcome, the impact of the supply disruption should it occur on the vertical axis, and this trade-off between probability of occurrence and the impact of occurrence should it occur. And so you have lines of roughly equal risk represented by these ISO risk or contour lines. Okay, finally, fourth perspective, what to do? I think in broad terms, the what to do is pretty obvious. It's some combination of three things. Produce more, enhancing and diversifying primary resource production. Wasting less, in other words, increasing manufacturing efficiency, increasing recycling, increasing reuse. And using less. Importantly developing substitute materials as opposed to just doing less in terms of smartphone use or whatever. So it's a combination of these three things that provide the solutions. In my view, the more interesting question is not so much what are the potential options, but how should we go about pursuing those options, and who should pursue them? These are my personal views. I have to say that because these are not the views of the Colorado School of Mines or the Department of Energy, which funds some of my research. I am an economist, and so I have to say, put myself at risk by saying, I believe we should rely largely on market forces, recognizing the time lags, but also focusing attention on what I would call and what most economists call the essential roles of government. And the idea really is the following. Once we've decided as a society which way we want the ship, the ocean liner, to go, economic incentives, if they work well, do a great job of optimizing behavior. And that's really what most economists believe in. And so if we think about optimizing behavior, we have 4 areas: improving and reducing restrictions on international trade when trade restrictions are the source of the supply chain risk, developing, I say, domestic resources. The idea there, this was written more for a national audience or thinking about national policy, but developing domestic resources when there are opportunities for domestic resource development. Information and strategic analysis. Governments play an essential role in collecting, assembling, and providing the information on which both public and private decisions are made, and in carrying out strategic analysis about climate change, about resource availability, about other important topics of social importance. And then finally, research and education throughout the entire supply chain of mineral resources all the way through materials and recycling. And so, final thoughts. Returning to the overriding question, will constraints on availability of critical raw materials limit the energy transition? My simple answer is possibly, but not if we pay attention now. Not if we pay attention now to the investments in geologic knowledge, in technological knowledge, in environmental improvement, and in managing the social impacts associated with resource extraction. Or if you prefer pictures rather than words, I like to think of critical raw materials as vitamins and spices capable of being obtained with proper investment as opposed to unobtainiums, as discussed in the movie Avatar, or highlighted by Avatar. And with that, thank you very much.